This exercise, question 10 to 3. Prove that the opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center of the circle. Let's create a quick diagram. The question here is the quadrilateral is circumscribing. Circumscribing means outside, inscribing means inside. Here, the quadrilateral is circumscribing the circle. So that means the quadrilateral is outside, the circle is inside. So I will first draw the circle and I will draw a quadrilateral so that it appears to be completely circumscribed. So that means the circle is completely fit within that quadrilateral. The quadrilateral is not very specific, no parallelogram, no square, no rectangle, nothing. Such that the four sides of the quadrilateral are perfectly tangent to that circle because the circle is inscribed. That's the biggest circle which we can fit within the quadrilateral. Now, let's name this as ABCD. Let's see the center of the circle as O. And I will first connect the center to the four vertices. And also, I will connect the center with the 4 points of tangencies. Now, so these are our constructions. Now, what is really asked is if I take a side AB, the angle subtended at the center will be AOB. And then I have to take the opposite side, which is CD. Angle subtended at the center will be DOC. These two angles will be supplementary angles. That means their total will be 180 degrees. Now, first we'll concentrate on these connections from the center to the point of tangency. We know that any tangent, which is in this case, any one side of the quadrilateral, when we connect that with the center, that will be at 90 degrees. So I have mentioned the four dotted lines at 90 degrees. That's a property of circle. Now, if I concentrate on these two angles will be equal. Why? Because first of all, these two smaller. Why? Because if you think about it, this dotted line is equal to this dotted line. This is 90 degrees. And this one is the hypotenuse of both triangles, which is common. So we can say that this smaller triangle is congruent with this smaller triangle using RHS, right angle triangle with hypotenuse and side equal. So that's why I will say this angle 1 is same as this angle 1 by CPCT, corresponding parts of congruent triangles. I can extend that logic and I can say that this 2 with angle matching with this 2, because I can repeat this process for these two triangles. I can repeat this process, this 3 equal to this 3. So any external point, if you draw two tangents and then if you make connection with the center, the triangles which you are going to make, they are going to be congruent. Let's repeat that 4 and 4. Now remember, our ultimate aim is to prove AOB from this shaded triangle and DOC, which is from this triangle, they are supplementary. That means their total addition is 180 degrees. So this angle is 1 plus 2 and this angle is 4 plus 3. If they are added, that should be 180 degrees. How we can proceed? First of all angles around point O should be adding to 360 degrees because they will form a complete one revolution. So I can say 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4, together that would be 360 degrees. So that means 1 plus 2 plus 3 plus 4 is going to be exactly half of that, which is 180 degrees. Now I will group them 1 plus 2 and then 3 plus 4. So now we know that 1 plus 2 is nothing but AOB and 3 plus 4 is nothing but this DOC. So I can say AOB plus COD equal to 180 degree supplementary angle. Is it also applicable for the remaining pair of angles? Yes, I can take this one again, and rather than combining 1 plus 2, I can combine 2 plus 3 and then 1 plus 4. Now 2 plus 3 is this angle so which is BOC, and 1 plus 4 is actually AOD. So this is equally applicable for any pair of sides as long as they are exactly opposite to each other.